Now that we've built a foundation for SLAM, we can talk about 3D reconstruction. 3D reconstruction is the process of capturing the shape and appearance of a scene or object. 3D reconstructions can be created through a variety of different technologies. In the case of the reconstruction here, we used a sequence of RGB and depth images, estimated the relative poses using SLAM, and generated the 3D reconstruction by reprojecting the points from the images back to 3D space. In general, 3D reconstruction comprises of the following parts. First, you need some sort of point cloud data. This could come in the form of a sequence of RGB or depth images from a camera, or maybe 360-degree LiDAR data from a 3D scanner. Depending on the type of data, additional steps are required before any sort of 3D reconstruction can be extracted. For instance, given a sequence of RGB and depth images, steps have to be taken to find the relative position of all the images. Next, we need to perform integration, or merging the images together. Then we can perform mesh extraction, pulling out vertices and triangles from point cloud data. Finally, additional improvements can be made to the mesh, such as simplification or texturing. First, pose estimation. SLAM allows us to align the images into a common space such that we can integrate them successfully. We often refer to this common space as the world coordinate system. Once we know the position of a frame, we can combine it with all the other images we've collected so far into some data structure. Once we have a pose estimated image, we need to convert the depth image to a point cloud in 3D space. Assuming we're using a pinhole camera, we use the intrinsic matrix to project pixels from the image to 3D space. The intrinsic matrix is unique to each camera and is a projection matrix from a pixel on an image plane to a 3D ray. We then use the depth data to find the pixel's actual position in 3D space. Once we have these point clouds, we need a way to integrate them or merge them together. A naive way of doing this would be to simply combine them into a larger point cloud containing the points from both smaller point clouds. However, this loses the context in which these point clouds are generated. The points are noisy measurements of a common surface. Therefore, it is more effective to merge and average the observations of different frames to develop a better representation of the scene. We implement integration using a data structure called the truncated signed distance function, or TSDF. The TSDF operates as follows. First, we divide the space evenly into voxels, or volume pixels. You can think of them as small cubes. Next, we retrieve a pose estimated depth image and project its pixels into a 3D point cloud. These pixels all lie on the surface of objects. Depth measurements are taken of surfaces, and empty spaces have no observation. Next, for each point, we draw the ray from the camera to the point. For voxels along the ray before the observation point, we assign a positive value representing the distance to the measurement. For voxels along the ray after the observation point, we assign a negative value representing the distance past the observation. So this is inside the object. In this representation, when voxels change signs, this indicates a surface lies there. As we take more observations, we average out the values of the voxels. In this manner, we can minimize the impact of noisy measurements as each voxel value becomes the average of many different samples. Another benefit of TSDF is its performance. Integrating frames with one another happens extremely quickly, enabling real-time 3D reconstruction. Once the TSDF has been filled with observations, a mesh can be extracted. The predominant mesh extraction algorithm is called marching cubes. Marching cubes is an algorithm developed by Lawrence and Klein in 1987 and uses the following technique to generate a mesh from a TSDF. For each voxel, we take the plus-minus value of each vertex, plus meaning outside an object and minus being inside an object, and perform a lookup based on the combination of the 8 vertices for the appropriate pre-computed mesh segment. There are only 2 to the power of 8, so 256, possible configurations for the vertices of a voxel, and many are rotations of others. The major benefit of using marching cubes is its speed, as it only requires one lookup per voxel and no other calculations. However, it results in a blocky texture, similar to that of Legos, due to the nature of the algorithm. This is counteracted by later steps of simplification as well as increasing the resolution of the reconstruction. When simply generating a 3D reconstructed mesh, the complexity of the mesh becomes very large very quickly. For reference, this small section of my house, recreated on the left, has over 4 million faces. For comparison, this scene from Crysis 3, a AAA game title, has only 3 million triangles. The reason behind this is the existence of many, many small triangles that simply comprise larger triangles. This is due to the process in which our mesh was created. Each voxel, each small cube of space, generates anywhere from 0 to 5 triangles in our final mesh. Clearly, there is some redundancy there. For example, the wall of the hallway in the left image is basically a rectangle, just a rectangular plane in 3D space. This can be ideally represented by only 2 triangles. 2 techniques to reduce the complexity of a mesh are quadric edge collapse and planar extraction. Quadric edge collapse seeks to reduce the amount of faces in a mesh by removing edges and merging faces that reduce the error in the mesh the least. We do this iteratively, and this approach can extract a simpler mesh with minimal trade-off. For specialized cases, such as the hallway in the previous slide, planar extraction is a useful mesh simplification technique. The goal of planar extraction is to detect planes in a point cloud, and using this data, we can assign a few large triangles to represent an entire plane instead of millions of small triangles. Mesh texturing further optimizes the use of the mesh in applications, easing the process of rendering a mesh. Texturing is the process of mapping each point on the mesh to a 2D UV coordinate, and then saving the mesh colors instead of in the vertices themselves. Instead, we would save it to an image, a 2D plane to be used later. Although not relevant to real-time reconstruction, for incorporation of a mesh into a scene, texturing is very important, both for performance and high-detailed texture information. Open3D, an open source 3D library, provides a texturing API for texturing meshes. One of the biggest hurdles to overcome in 3D reconstruction is the ability to perform the reconstruction in real time. With long computation times and endless memory, offline reconstruction is an art on its own and can be optimized to the point of perfection. However, in real-time 3D reconstruction, trade-offs have to be made for speed and memory efficiency. With real-time reconstruction, new frontiers of AR can be explored. One such application is HoloLens holoportation, Microsoft's technology that brings live 3D reconstructions of people into your living room via the HoloLens. An array of sensors takes measurements of one person, performs 3D reconstruction, and sends it to another person's HoloLens, allowing them to interact as if they were there. When dealing with real-time 3D reconstruction, we run into the issue of scalability. When performing offline reconstruction, once the data has already been collected in its entirety, the extent of the reconstructed scene can be calculated beforehand. During real-time 3D reconstruction, however, the system must be able to scale almost indefinitely. In order to achieve this, we perform several upgrades on naive TSDF. One major weakness of traditional TSDF is the issue of rigid space allocation. Because we divide the real scene into voxels of fixed side length, we must decide the overall dimensions of our scene upon the creation of the TSDF data structure, and many of these voxels will end up being empty because they represent empty space. One possible solution for this problem is a hashing function that assigns a value to sections of the real scene, each containing multiple voxels. This is called voxel hashing. Each one of these sections can be thought of as its own TSDF. In this way, the scene can grow dynamically as more parts of the scene are discovered and placed in the hash table. Also, parts of the scene that don't include surfaces won't be generated, so we can save space there as well. This allows a much more efficient and scalable TSDF representation. The implementation we use is derived from the elastic reconstruction system. Another solution to the scalability of TSDFs is mesh blocking, where every time the camera has moved a certain distance, a mesh is extracted and solidified, and the TSDF is reinitialized with the current camera position as its center. In this way, real-time reconstruction can be extended much longer. However, with the drawback that earlier sections of the mesh are now immutable. This also helps with speed, as the size of the TSDF we keep is limited, and we only need to perform minimal extraction. The attachment between blocks of mesh and keyframes is key to the speed increase and malleability of the real-time reconstruction pipeline. The rendering process of previous mesh blocks includes a step that checks each keyframe's position and location as estimated by the SLAM system and transforms the mesh appropriately. As we said before, loop closure can change camera poses from places we were in the past. As SLAM continually optimizes these poses and locations of past frames, the mesh blocks align more accurately with the real scene. In addition to the open source libraries required to run SLAM, which is also used during real-time 3D reconstruction, Open3D is another open source library used for OpenARK. The specific functionality provided by Open3D are the TSDF, or truncated sign distance function, the data structure used for integration of camera frames, mesh extraction, the implementation of Martian cubes, and voxel hashing, the spatial hashing function used to expand the scalability of TSDF. The SLAM dependencies are also listed here for convenience. One of the limitations of real-time reconstruction is the rapidly increasing computation complexity when the resolution of the mesh increases. For consideration, a room constructed at a resolution of 1 centimeter may have millions of triangles, while the same room reconstructed at a resolution of 3 centimeters will only have 10,000 triangles, a much more reasonable number to render and integrate to in real time. Also, in real time, optimizations to earlier portions of the mesh arising from loop closures are difficult to deal with, and oftentimes expensive operations are required, such as deintegration and reintegration of previous frames affected by pose optimizations. Therefore, OpenARK's 3D reconstruction module is broken up into two parts, an online and offline part. The online part runs real-time reconstruction at a lower resolution with the goal of providing the user a visualization of the current scanning process. The data is saved at the same time, and then the scene can be reconstructed at a very fine resolution once SLAM has stopped running and the poses have been finalized and optimized. The real-time 3D reconstruction demo has the following structure. As with the SLAM demo, first we initialize a camera object, specific to whichever camera we are using to run OpenARK. Then the SLAM system is initialized. Callback functions are passed into the SLAM system to combine both all the SLAM and 3D reconstruction maps. Then the main loop is run. When the output of SLAM is received and a pose has been estimated for a new frame, it is passed into the 3D reconstruction system for integration. It is also passed into the saving system for saving to be reconstructed later offline. Loop closures are also detected from the SLAM system, and the transformation of older mesh blocks inside the 3D reconstruction system are updated accordingly. The following screen captures are the results from our real-time 3D reconstruction algorithm. The code was run on a Microsoft Surface Pro, and the scene was captured in one cursory pass using a single RealSense D435i camera. The reconstruction required real-time integration, mesh extraction, and rendering. The data was also saved for later offline reconstruction. The integration was run at 10 Hz, and the mesh extraction was run at 1 Hz. One thing of note is that since the 3D reconstructions come from a single camera, gaps in the scene are inevitable, unless one is extremely careful about their scanning technique. Also, the back sides of objects in the scene will inevitably be incomplete as they are fully occluded. These screenshots here depict the difference between real-time and offline reconstruction quality. The image on the left, taken from a 3D reconstruction run at a resolution of 3 centimeters, exhibits many of the weaknesses of the Martian cubes algorithm. The surfaces of the scene are very blocky and have imprecise geometry. The image on the right, taken from an offline 3D reconstruction run at a resolution of 0.5 centimeters, shows the effect of simply increasing the resolution of the reconstruction on the performance of marching cubes. For comparison, the image on the left has 10,000 faces, and the image on the right has 9 million faces.